back to the screen, we'll move on and start taking a look at mechanisms. Can you hear me alright? I was messing with the audio when we were off. Okay. Alright, so we've talked quite a lot about chassis. We've talked about what goes into building them, what they look like, what you have to do to design one. Now we have to look at what we're actually going to, or what we would actually have to do to design the game challenge mechanism. So, do we have to pick up balls? Do we have to move hoops? Do we have to shoot something out into a goal? All of those things have to be done using some way to manipulate a game piece other than actually moving the robot around. And this is the same in any other use for a robot as well. In fact, there are some types of robots, usually industrial robots, that specifically don't have a way to move around. They are fixed in one place and are nothing but the manipulators. So if we look here, there's essentially two specific types of mechanisms for a robot. There's an arm of some type, and then there's a lift of some type. And then there's a combination of the two. And this isn't really even talking about grasping or anything like that. So being able to grab a frisbee off the ground or pick up a wiffle ball or something like that. This is simply moving the arm around and what you have to think about in order to create them. So arms in specific is our first one. Okay. So arms consist of a pivot point, a bar, and an actuator. Being powered traditionally by either a motor or a set of pneumatics, they allow for rotation about a given point for the end of the arm. Typically, the torque need is large, as such, teams need powerful motors or pneumatics to move them effectively. Both arms and linkages will need software or hardware stops to prevent them from breaking themselves. So what that means essentially is that if you create something like the arm that we see in the picture over here, excuse me, this particular arm looks like it is probably pneumatically actuated, which means it uses compressed air, at least in the terms of first robotics, it has to be compressed air. Other places that don't have such strict regulations could have what are called hydraulics instead. So instead of using air, you would use a liquid of some kind, because liquid in a pressure system won't compress quite the same way that air will. I mean, it will compress, but not nearly as much. And it's that compression that allows the fluid, either the air or the water, to to move an actuator. So if we look here, arm forces, angles, and torque. Torque is a measurement, essentially. It's a mathematical formula that talks about the force required to push something and the distance that it is pushing it. So the same force at a different angle will need more or less torque depending on the distance required. I am sorry, guys. I cannot stop yawning. I will try not to interrupt too much with this. But, so for example, it's going to take a great deal more torque to move the first example, this side over here, than it would to move this one over here, even though it's moving both the same 10 pounds. And the reason for this is because the distance between your pivot point, which is this section up here, and your weight is much more. If you think about it as in, say, if you pick up a 25-pound dumbbell or something, it takes a lot more force to get your arm probably about past 45 degrees through the next 90 degrees than it would to move up here or to move down here. And the reason for that is if this is your pivot point and your muscles are your actuators, then the arm, the distance from that pivot point, is so much greater. And then real world examples, which is essentially what I just said. Same force at a different angle needs more or less torque. The weight held at arm's length will require more effort due to the greater distance. Okay, so an arm power example. The same torque with twice the power results in twice the speed. So power is a measurement that is torque divided by time. So you want to be conservative in designing a safety factor of about 2 or 4 times. And what we're talking about there is you don't want to if you put too much speed into a system, there's a good chance that it's either going to throw the object that you're trying to hold, or it's going to not be able to stop itself, and it's going to break something. Um, so here what we have here, we have 120 watts and 100 revolutions per minute. That's less power and less speed. And on the other side, we have more power and more speed, which gives us a higher wattage and a higher RPM. Now, one general rule is that let's see here if we talk about it. No, we don't. So one general rule that you have to think about though is that generally the more torque you have in a system, the less speed you're going to have. Um, and the reason for that is because more power is being applied to make the motor turn harder. There is basically a failure point in every motor where you have so much force on it that instead of continuing being able to lift up, it's going to fail and either stop in that position that the weight and torque balance out with the power being given to it, or it's going to break loose entirely and fall down. That doesn't mean it's broken, but it does mean that it's going to no longer continue trying to force itself up. Um, Now, there are different gearboxes that you can get. In fact, the whole point of a lot of the gearboxes that we use is to increase the torque of a motor. There's a whole chart that that I have in the shop that I didn't think to take a picture of, but it gives and that stopping point is called its stall weight or stall torque basically, and that's at the point that's the failure point of the motor. Um, but essentially, the gearboxes take what is a very fast spinning motor with very little torque um, because of the speed and changes it up so that you have a slower motor, but you have a lot more workable power with it. And then here is the real world example here. We have less power and less speed versus more power and more speed. Um, let's see here. Stronger is often faster when it comes to handling demanding tasks, at least until it's actually trying to handle those tasks. So it'll be a lot faster until it gets a significant load on it, at which point it'll slow down, but it'll still be able to handle that task. Okay, so we've come up with, so that's basically how you would have to design an arm. The problem is there are usually physical stops in place, or there are maximum limits that will make it so that if you go beyond them, some of the physical hardware will break, especially if it's something that's not plastic, or something that is plastic. So you have to come up with what are called work envelopes. And a work envelope is essentially the range of motion that is designed into something so that it will be able to work effectively and repeatedly without being broken or injuring somebody. These distances are determined by the length of the robot's arm and the design of its axes. Each axis contributes its own range of motion, and the more axes a robot has, that will increase the size of its work envelope. It's often possible for a mechanism to move beyond its physical limits thus damaging itself in the process. And I have a very good example of this that I'll tell you in just a second. But typically, this is achieved, or typically there is limiting that is involved that are achieved with sensors and limit switches and encoders. And we'll talk more about those specific sensors later on. But for my particular example here, I've been working on upgrading our laser engraver in the shop, and it's a machine that uses what are called stepper motors to move what's essentially a pointer head around a surface, and that pointer head is what emits the cutting laser after it does a few other things, or like so. Without getting into the full mechanics of how a laser works, there's a tube in the back that energizes light to an extremely high power and temperature, and then it gets bounced through mirrors through the inside of the machine until it comes to the laser head that directs it down to the surface that you're cutting. But the way that the laser itself works is separate from the way the mechanism works. So any Cartesian system, and I know that's a new term for you here, but almost every robot system that we have, except for a few very specific examples, work off what's called a Cartesian coordinate system. You've probably heard that in math. It's essentially an x and a y axis with denoted grids. And those grids are positive or negative depending on where your origin is. So for the laser, at least this laser that I have specifically, the origin is in the upper right hand corner. So if you think about that in terms of a coordinate system like you've used in math, then the entire work surface of the laser is in the negative x and negative y quadrant of a grid. And that's not a problem, and that's not what I was working to change. It's something that is built into the software to know that. Well, one of the things I changed was the brain of the laser. And when I did that, I didn't know that the brain that I had replaced it with thought that the upper left-hand corner was the origin. So that's where 0, 0 was. And it was designed to work in a positive x and negative y axis. So when I turn the machine on, both the x-axis and the y-axis started to move to that far corner. It wasn't a problem for the y-axis, which is the up and down version in the laser, because that's what it was supposed to do. It was a problem for the x-axis. The limit switch that's built into it that says, hey, you need to stop here or you're going to run into the wall, was on the other side of the machine. And before I could get it turned off, the x-axis had moved all the way over, hit the physical limitation of its space on the side, and when that happened, it overloaded the stepper motor, which didn't damage the motor, but it did. It did overload the power supply. Now, I attempted to, or rather, it blew a fuse that was built into the power supply, and that's what I have on the screen right now. So this is the power supply. I've taken it apart. It had a fuse that was built into its system right here. Excuse me. That was completely kaput. There was no fixing it because it was basically a cylinder fuse that was soldered into the machine. Now, I looked on the internet to find ways to fix it, and they said just solder in some clips in the place of the fuse and then put a car fuse in front of it. Which that part worked okay. However, and this is where translating from other languages can be a problem, the document I was looking at had been translated from Chinese, and it said that I needed to put a 15 amp fuse in it. That's what I did. Except the problem is the translation was wrong and it should have been 1.5 amps. So I had myself a nice little electrical fire in the power supply for it. So that is one thing that can happen when you go beyond the physical limits, is that it can overload the electronics that you're using in the robot. Now, all of our robots have much more robust fuses built into them, and they're resettable ones. So you click a switch, and it resets the fuse so that it works again. This was never designed for that. In fact, the replacement that I've got that comes in tomorrow is a much more robust system that should, if this happens again, allow that to not happen. But anyway, that is why there are limit switches built into the laser, and that's why you have to think about think about how the switches and how you define the limits of your robot. So the picture on here that's kind of over in this corner is of an industrial robot. It would be one that had been mounted to a surface, and then it has a base range of motion down here at the bottom that looks like it can go roughly 180 degrees. And then it has another range of motion up here, another one up here at the top, and then finally another one that doesn't look like it's connected to anything at the moment. So these different ranges of motions have to work together in order to figure out where the arm is in 3D space, and so it doesn't crash and break itself. For example, with this one, if this robot, and this is a programming problem more than anything, because all of these probably have limit switches built into them, or more likely what's called an encoder, and I'll talk about those in just a second, built into it so that it knows at which angle each motor is, and the programming would say, if this motor is at this angle, then this one can swing between these specific angles. But if it's a different one, then that would change. I know that sounds confusing, but it's really essentially a mathematical table that we'll learn more about when we start talking about actual programming a little ways down the road. Okay. There we go. All right, so ARM design tips, since I changed the slide and then didn't really actually use the slide for what it was talking about. Lightweight materials are the best. Design sensors for feedback and control, that's the limit switches in the envelope. Linkages help control long arms. Keep things as simple as possible. So the less parts you have to build, the less parts that you have to replace should they break. It's easier to operate, it's more robust. Use off-the-shelf items if possible, because custom-made ones are harder to design for. And then having counterbalances, such as springs or weights on the other end, are very helpful as well. If you guys have used a higher-end telescope that's kind of heavier, generally you'll have a counterbalance on the other end of it to offset the weight at the pivot point. Generally, when you're coming to robot design, you don't do that very often, simply because it'll get in the way and it doesn't serve much in the way of function. So you'll counterbalance with springs or stretch bands or something like that. So here is a type of arm linkage that's simple to create. It has its built-in limits, essentially. So this particular one here can stretch between putting this triangle on the floor and raising it this high in the air because of how far apart these two bars are, or the 4-bar linkages. As you apply pressure to this section here, so like if you were to put a pneumatic actuator right here and push out on it, then that simple angled push is going to cause the pivots on both parts to pivot, and it provides a more stable arm that's stronger and creates the movement that you're looking for. So a four bar linkage is very similar to an arm, but the fourth bar will always remain vertical and in orientation, and as a result, the force of distribution, the weight will be applied to the pivot points between the bars, and that can be very high. The upper bar will always be tensioned. As a result, the fourth bar, they're limited in rotation. Both arms and linkages will need software or hard stops to prevent them from breaking. This is one of those situations like I was talking about. If you push too hard and these pieces of... I'm sorry, I forgot I have a pointer. These pieces of metal here, or wood or plastic or whatever they are, run into each other and then you keep pushing at them, either they're going to break or the pivots themselves are going to bend. Which I've seen robots bend steel bolts before, like thick ones, half-inch thick steel, because the hard stops didn't work right. So again, some tips for 4 bars. Use lightweight materials, design in sensor and controls, control long arms with linkages, keep things simple, the less parts to build. So basically, all arms have essentially the same basic tips for them. If you look at this one here, it's a 4 bar linkage, but it also has what looks like some surgical tubing, and that's the stretch stuff that we usually use to help pull it back into place whenever you're done with whatever the activity's holding view is there. So here is an interesting one. This is extreme, basically the most extreme version of this that I've seen. But it has, this was back when they were doing, I think it was logo recovery. Essentially, you had 3 air inner tubes, like you would take swimming with you, essentially. And they were in the different shapes of the parts of the first Lego, the triangle, the square, and the circle. And you had to put them in order on a rack that was like 8 feet in the air, or something like that. But you had to start inside of a very small cube, and this was one of the most successful. I think they actually were the champions that year. But this is one of the most successful designs. They have 4 bar linkages that lift up this section. Then they also lift this section, the higher it goes. And then finally, they lift this section. And everything is based on the torque output of these actuators down here at the bottom. They get pushed up, as you can see in the... Make that go away. How do I make that go away? Go away. Come on. Can't. Nope. There we go. So down here at the bottom, and if I move my mouse, it's going to make that thing pop up again. But you can see the yellow linkage arms are pointing straight down. And this is when the whole thing is cocooned together inside of its starting shape. Once they start to push out, they're lifting the actuators here that is raising the first stage of movement. Generally, when we're talking about arms and lifts and stuff like that in robotics, you always have a fixed position, something that starts and is either there as a function to hold it in place to start with or to be your mounting point for your motors. That'll always be called stage 0. And then your first movement part will be 1, 2, 3, 4, or however many moving parts you have after that. So in this case, our stage 0 is the vertical bars here at the front edge. As that actuator lifts up, stage 1 gets pushed up. And because of the physical linkages between stage 2 and 3, it starts to expand out as well. Until finally you get over here at the end, the thing is fully extended, almost 3 times, if not more, the original height. And that's basically how that particular lift arm works. The other thing is elevators and lifts. This particular robot is from that's on our picture here is from Recycle Rush. I believe that was the 2014 competition. But you had to do a whole bunch of different things. You had to pick up these gray totes and move them around. You had to pick up trash cans, and you also had to be able to pick up and throw basically pool noodles and stack things very high up. So there were a lot of very tall, very innovative robots, and this is a good example of the design of one of them. If you're wanting to gauge a size here, these wheels at the bottom are probably about 4 inches in diameter. Okay. So lift elevators are the first one we're going to look at. Elevators in FRC are fast, efficient vertical movement and usually consist of the following. They'll have a carriage of some kind and a track. Sometimes you'll have multiple stages. So two-stage elevators, depending on the maximum height for the starting position and the objective of the game, it may be necessary to design a two-stage lift, like the one shown at the right. Two-stage lifts feature an additional intermediate frame section, and both move with a stationary track while acting as a carriage at the same time. Let me see if I can find a good example of the one that we built a couple of years ago. Because we had a couple of different designs for a couple of different years that were very much inspired, or that very much used this system. Edu Gus dot. To remember what my SBRUMBH at p gus dot pit e.edu. There we go. Find my password real quick. One problem with having your accounts hacked and then going through and making sure that everything is secure is that you tend to turn on all of the safety precautions, which is kind of a pain in the neck. There we go. Show. Alright. Which means you have to use the authenticators, and it's always kind of annoying, even though I wouldn't want to have to go through trying to reclaim all of my accounts again after somebody hacked them. Save. Turn on sync. There we go. We would like to confirm it's you. Yes, it is me. That was dumb. So PHOTO. Yes, come on, just load. Let's see here. Photos. And let's see here. Nope, wrong place. Alright, so here's a good example of an arm. So this was most of the robot that we built for, actually, I think the game that you are designing for right now. This was the middle school robotics team's prototype from 2018. So this would have been Rover Ruckus. It had this arm over the top that was chain driven. It flipped back and forth and was able to pick up and scoop the ball off the ground. So interesting. I wouldn't recommend it though. This was very complicated and had several design flaws. We kept breaking the arm at the front because they did not program in any limit switches, but that's not why I'm here. Let's see here. Robotics. Is this? Yep, that's the frame lifter. Student driver. Sorry, we've done a lot of robots. So here's the insides of one of our robot a few years ago, or from a few years ago. We used mechanism wheels. This is all the electronics, which we'll get into talking about later. However, it's not the one I'm looking for because this one does not have the lift mechanism in it. How about this one? Nope, that's still student driver. We tend to name our robots depending on what's going on in a particular year. You know what? I'll find the correct album and show them to you at a later date, because that just randomly picking through my files isn't going to find them. But anyway, you have your stage 0, you have stage 1, which is the center carriage right here. It moves up and down and then acts as the track for stage 2, which is the actual carriage itself. So each preceding stage gets bigger from the carriage, but you were able to extend up even higher. Now, you can do this a couple of different ways as you link them together. You can start off by having one rope that gets connected to a power source. It goes up, and then down to your chassis, so it gets linked through a couple of different pulleys. And in that situation, ideally, your carriage, the inside one, raises all the way to its top extent. And once that happens, then it pulls the second stage up so that you get taller based on the movement of the first carriage. And that one works, but it puts an insane amount of torque on that one motor. So the better way to go about this is to take your motor and attach it through one pulley at the top and to the bottom of your first stage. And then you have a wire that's bolted into your first stage that goes over another pulley and gets bolted into your second stage. So what happens now is that one motor is actually only pulling on one point instead of going through a number of pulleys, which increases the torque that is required. The difference here is that the entire mechanism moves as one unit. So you have your your carriage that's in the middle. If you pull, let's say, a foot full of wire, so if you move a foot upwards, then you're actually going to get 2 feet of movement because your first stage is going to go up a foot, but your carriage is also going to move up that same distance on the inside. And they kind of telescope together, which my hands on your little camera are probably not a very good descriptor of this. But it's much easier to make it more accurate, or to make it easier to pull up and down. It's just harder to make accurate, I guess, without a lot of programming. I wonder how far off the topic I got here. Oh, yeah. This is continuous lift. That's the one I was describing, where you have one pull motor that's going through the loop systems up to the top. And then this one also has some stretchy tubing here that pulls it back down again. That's one problem that you run into when you have an extended lift system like this. So instead of nesting them one inside of the other, they're basically front to back. And when that happens, the further they extend up, the more forward pressure there is on it, and it causes a lot more friction. This was the other one I was talking about, the cascading lift. So we have our motor that is just pulling up our first stage, a stationary rope that's pulling up our second stage, and then another stationary rope that's pulling up the carriage in this particular one. This says it produces a greater load on the motor, which isn't untrue. It's just you have such a reduction in friction that the torque required is much less. This would be the way I would always recommend doing this because we've never had much in the way of luck with a continuous lift system. We've only really had luck with cascading lifts. Some of that comes down to accuracy in manufacturing techniques, though, and the fact that we don't have that. Okay, so elevator and lift tips. Most error and stop play comes from the sides. So if you put time and effort into these to ensure that they're robust yet reliable and slide freely, you're going to have a much easier time with this. Test the design for how little overlap you can get away with between stages. This means that you can get taller with less material. It says that 20% is a good starting point for a minimum overlap. Uh, so, for example, if you have a height of 50 inches in your first stage of lift, and your second stage is also 50 inches, you can't make it 100 inches tall because then it's just going to fall off. You would have to take 20% of that height for overlap, which means you start at 50 inches and then you are only 80 inches tall when you're fully extended. Um, and then you can add another extension if you need to get taller than that. But that overlap it really is a good minimum. There are two ways to rig an elevator, which we talked about, was continuous or cascade. Drive cables up and down, or have some way to force the system back down. So we use stretchy cables or stretchy surgical tubing quite a lot. There are some continuous drive systems, which that would be terrible to design. That you can create using chain. So instead of having a carbide rope or something like that going over your pulley, instead you have a sprocket in place of the pulley and a chain that is in a continuous loop between another pulley at the bottom and a sprocket on the motor. Or when I said pulley there, I meant sprocket, and then a sprocket on the motor as well. So when you turn in one direction, it's going to lift the first stage up, and when you turn the other direction, it's going to pull it all back down again. Which is probably the most robust way of doing this, but it's also, speaking as somebody who's used chain quite a bit, is a real pain in the neck. Chain isn't very forgiving to tolerance issues. Anyway, consider adding a brake system, such as so some motors have what's called dynamic braking built into them. They will back drive a little bit to stop something from moving and to hold it into place. The best example of that is something called a stepper motor that essentially has two motors built into it, and it will move them a little bit at a time and then lock it in place so you can't move it out of place. In fact, every time I've had the 3D printer running, you'll hear the stepper motors whining because they are basically a pulsed drive, which just means they continually kick one another forward. And then adding sensor feedback to prevent damage is also very helpful. In this, it talks about using a Hall effects sensor or limit switches. So we haven't talked about sensors a whole lot yet, other than the fact that they exist and you need to think about it. But essentially, we've talked. So an encoder is a magnet that's on the shaft of a motor, and it counts the number of revolutions. So you can say, hey, I want you to go 15 revolutions. You can calculate how far that is, and you can put in to the programming, I want you to move 15 feet forward, and then it will do that number of revolutions to reach that far. However, that doesn't really stop you unless you have dynamic braking built into the robot. A Hall effect sensor is essentially a light. It blink or when you get close to it. Oh, there we go. When you get close to something like, well, I guess it also works with sonar too, which we have those as well. But once you get close to something, it'll recognize that you're getting closer and stop the motor at that point. Or there's actually a limit switch, which when you click it, it breaks the connection and stops something from moving any further. Those are usually plugged into, there's a couple different places. You can plug them into your motor controller if it's one of the more advanced ones, or it's plugged into a spot on your robot's brain. And lastly, let's look at rack and pinions. So a rack and pinion is essentially a motor with a gear attached to it, and it runs against a track or a pin or a rack, excuse me, that has the same tooth spacing as the gear, but lets you move up and down, except it's flat. It's not on a curved surface. It's very heavy and usually pretty expensive. However, it is one of the most precise options there are, because you can tell it, I want you to turn 15 revolutions, the motor, and you will go 15 revolutions and stop. It holds into place very well. It's very robust and good at carrying heavy loads. What is going on with this thing? It's like anytime somebody tries to get in, it just doesn't want to let people in. Zoom's having a rough time today. Sorry about that. I clicked admit several times and it just wouldn't let you in. But you're good now. Sorry. The drive gear must be mounted where the linear slides overlap, so that's what we've got going on right here. This section right here is essentially probably a piece of square tubing that mounts the motor to it and holds it in place. It needs to be at the top. That way you have the most range of motion that you can get. One big problem with these though is there's not really an easy way to stop it if something goes wrong. The pinion will actually feed all the way out of the top and fall out of the machine. Sometimes that's a good thing for maintenance, though. You can have it walk its way all the way out, and you can take that whole piece off to work on it if you need to, and then very easily put it back in. But that's about the only good solution or good time you would have that happen. And then we have the scissor lift. And the scissor lift is one of the most complicated things to design. They are very good at getting very tall from a very small starting point. But there are a lot of forces involved. We did attempt to make a robot using a scissor lift 2 years ago. However, we used some unorthodox material and it kind of failed miserably. We'll talk more about that when we come to what not to build a robot out of later on. Has a large number of independent linkages bound together to reach high areas. They don't handle side loads very well, so once they start to get tall, they'll wobble back and forth like this a little bit, and they're not great at being extended when you're moving, especially for accuracy, for the same reason. Like, they have very good front to back stability, but side to side will wobble pretty terribly. When the bottom of the scissors is pulled together, it extends up. So in this example, there's a rack and pinion sitting down here with the motor sitting on the first leg of our lift. As they move along the rack, or as it moves along the rack, it lifts straight vertically. They are very good at smaller robots, though, as long as you have the materials to make them out of. So if you're making something that's only going up a couple of feet, there's a very good chance that this is a good solution, because then you don't have you can manage it by using stronger materials. You can manage that sway, or it isn't really that much of an issue. It's only when you get really tall that it's a problem. The pros is the minimum height reached can go under field barriers. So in this case, if you have to go under something that's really short, you can get there very easy. But it tends to be heavy. When you make it stable enough to be used, it doesn't like side loads. It must be very precisely built, which was one of our problems when we created it. The higher you go, the less stable it is, and loads that are very high tend to tend to have a hard time getting to a point. There's a tipping point where you go from having a hard time trying to push it together so that it lifts up to moving up very quickly after you reach that tipping point. Let's see here. Okay, we got two left. Then there's lead screws. These are pretty interesting ones. I've actually designed and mostly 3D printed one that I have sitting over here. So a few years ago, before I found a website dedicated to selling the parts to easily create your own computer-controlled cutting apparatus, I started designing one that I could print and build myself here with equipment that I had on hand. This was going to be what's called my Z-axis. So I would attach my cutting head, which in this case was going to be a computer router, to the front end of this, and then I would put a motor here at the top, and it would raise and lower this so that the cutting head would move down into the material that I'm trying to cut. It's very, very robust. You can put a whole lot of weight on this and get it to lift in a very controlled manner. Now this one has been used for quite a while as a demonstration piece, so I don't know if you can actually see it, but, well, here, just a second. So it's kind of losing some of its stability, but if we were to look at this close up, right here, you can see that this has quite a bit of wiggle to it now. And that's something that happens as plastic parts, and indeed many parts, start to wear. So this would have been ended up being machined out of a block of aluminum instead of a 3D printed piece. But I had to actually have something in place so that I could make the machine basically make itself. So this wouldn't have been the final part of this project. But this is a lead screw. It's pretty precise. You can lock it in place very easily. It's simple to build. You just need some sort of a tracking system, and then threaded rods, and then a thing to actually, a carriage to actually move the threaded rods. Can be pretty slow though. We used lead screws a couple years ago to lift our robot off the ground, and they were just really slow. They can be pretty heavy, and unless you have a very thickly diametered drive shaft, they can have what's called backlash, where as you're trying to twist it, it'll start to bow a little bit and then bend backwards. But they're still very useful. The CNC that I ended up actually building has an upgrade that should be somewhere in the mail at this point that will convert its belt-driven X and Y axis to a lead screw version, which is a lot stronger. And then we have what are called ball screws. It's essentially like this, but instead of having this threaded collar in the middle of it, you have an apparatus that has what essentially looks like a whole bunch of BBs on the inside of it. Those BBs ride inside of this track and they make a much stronger, smoother transition up and down the carriage than you get just using the plastic lead screws. That being said, I mean, if you watch this, if I was to let this go, it's going to transition all the way down on its own. So there's not a lot of friction, depending on depending on the plastic that it's made out of. Ball screws can be very precise. They backdrive very easily, which is a good thing, but only if you want it to do that. But it is very noisy, it's complicated to make, and then it's also backdrive very easily if you don't want it to do that. And this example that we're looking at here appears to be a type of CNC where you just set it on top of the surface that you want to do your cutting on, instead of moving the wood that you want to cut into a machine. But and then that's where we're going to stop for today. And then hybrid designs are essentially merging the two, so you have an arm attached to the carriage of your lifting mechanism. So that's where the next part of this project is for you guys. You need to come up with what you want to do for an arm or lifting mechanism. Start thinking about how you want to grasp the cubes or the whatever the cubes or the little wiffle balls, the minerals, according to the game manual. And then we still need to look at how you're going to hold that and transport it, but that's something that we can do afterwards. So you don't have to use a lift gate, you don't have to use an arm. You can use some combination of the two. If you have some idea that we didn't even talk about, discuss it. See if that's going to work with your group. But let's see here. That's essentially the end of class. We've only got about 8 minutes left. But on Thursday when we meet again, it's going to be more group work time, so that you can talk this out then. You're free to do that beforehand, in between. But yeah, I think that's where we're at for now. If you guys have any questions, let me know. And if not, enjoy the rest of your Tuesday, and we'll see you next time. Okay?